All right, so the theme for this video is the matrix, because we are talking about the matrix equation. And if you don't know about the matrix, then that makes me feel really old, and that's okay. But the Matrix was like one of the cool movies when I was growing up. So the matrix equation that we're looking at is AX equals B, where A is a matrix, X is a vector, and B is a vector. So when we multiply A by this vector X, then we're going to get B, which is a vector. So, our definition, if we have an n by n matrix A with columns, which are A subscripts, those are column vectors, and if X is a vector in our n space, so X is going to be an n by 1 matrix, then the product of A and X, denoted by AX, is the linear combination of those columns of A using the corresponding entries in X as weights. So when we have AX like that, we're taking our X1, and that's what we're weighting on our column of A, and then we're adding each of those up with their respective weighted columns of A. That is what we are doing when we are taking A, the n by n matrix, and multiplying it by X, an n by 1 matrix. So we can have an m by n matrix A that we're multiplying by an n by 1 matrix X. And that is allowed because our inside dimensions match up. So we have the right number of columns in our first part that match the number of rows in our second part. So, for example, if we have a matrix A that is the entries 1, 2, -1, 0, -5, 3, and we have this matrix, this n by 1, this 3 by 1 matrix X, that means that we're going to, in order to multiply, we are going to weight our columns of A with the corresponding weight of X. So this is X1, X2, and X3. So we have 4 times 1, 0, 3 times 2, -5, and 7 times -1, 3. And so when we get that, well, scalar multiplication works the way we think it will. So we get 4, 0, plus 3 times 2 is 6, and then -15, and -7, and 21. And then we can add up those corresponding entries. So we're just adding up our first entry. So we got 4 plus 6 plus -7 is 3. And then 0 plus -15 plus 21 is 6. So the result is 3, 6 as our vector. So AX equals B, where in this case our vector B is 3, 6. Alrighty. Let's do another example. And remember, we need to take the weights. So 4 is going to be the weight on our first column, and 7 is going to be the weight on our second column. So we got 2, 8, -5, and -3, 0, 2. So when we just scalar multiply what's on the inside, we get that for the first one, and that for the second, and then add them all up, and I think we get, let's see, -1, 3, 32, and -6, I think. Yeah? Alright, cool. So that's AX equals B, and we get out a vector, and the resulting vector that we get, our vector B, is going to be the size because this was a 3 by 2 matrix that we're multiplying by a 2 by 1 matrix, so a result is going to be a 3 by 1 matrix, because the middle has to match up in order for us to have the right number of weights. And then what we're left with, the dimensions of our resulting vector, is going to be 3 by 1, which are the outsides. Alright, so for vector 1, 2, and 3 in our M space, write the linear combination 3v1 minus 5v2 plus 7v3 as a matrix times a vector. So we need a matrix A, and that's going to be made up of our vectors v1, v2, and v3. And since we're handwriting, I'm going to throw the little vector symbol on top to show that these are each vectors. And we're multiplying by what? We need to weight v1 by 3, we need to weight v2 by negative 5, and we need to weight v3 by 7. So that gives us a x. Our matrix A is made up of our vectors v, our v vectors, and our column vector x is made up of the weights 3, negative 5, and 7. So we got vectors times weights, and that's one way we can write it, and here's another way we can write it. So here's a theorem. Sorry that we don't have fun names for theorems. If A is an m by n matrix with the columns A1 to AN, and B is in our M space, so an m by 1 matrix, then the matrix equation AX equals B has the same solution set as this linear combination of our corresponding entries. So that in turn actually has the same solution set as our system of linear equations with this augmented matrix, where we can just forego our x's entirely because the locations in our augmented matrix show us what those weights are, what those x values are. And then in line with this, the equation AX equals B has a solution if and only if B can be written as a linear combination of our columns of A, which is saying the same thing that this is saying. So, how can we figure out, for example 3, if we have this matrix A and this vector B, is the equation AX equals B consistent for all the possible values of our B's, B1, B2, and B3? So, I mean, you might prefer a different way, but I think the easiest way to tackle this is by looking at an augmented matrix where we have 1, 3, 4, and negative 4, 2, negative 6, negative 3, negative 2, negative 7, and then B1, B2, and B3. So once we have this augmented matrix, we can do some row operations to give us, we can do row ops in order to get to a echelon form, and that can help us to see if a solution exists, or if there's infinitely many solutions, or if we have an inconsistent system. So, let's see, what should we do? Well, we can take, I like this one is nice. Just keep that there. And then we have 1, 3, 4, B1. Let's take 4 of our row 1s, add them to row 2. And so we get 0, 14, 4 times 4 is 16, minus 6 is 10, and then we have 4 B1s plus B2. And then, for our last row, let's take a 3 times our first row, add it to our last row. So we get 0, 3 times 3 is 9, minus 2 is 7, 3 times 4 is 12, minus 7 is 5, and 3 times B1 plus B3 is our last entry. All right. This is promising because now we have a 14 and a 7, so we don't necessarily have to divide things out. So let's see, what do we get? We can copy this down, 1, 3, 4, B1, 0, 14, 10, and 4, B1 plus B2. And if we take row 2, multiply by negative 1/2, and then add it to row 3, then we should be good to go. So we got 0, 0, 10 times negative 2, negative 1/2 is negative 5, so that gives us a 0 there, and oh no, this might not be 0. We have, what is this? Negative 2b1 plus negative b2 over 2 plus this 3b1 plus b3, just taking negative 1/2 of this part. I guess I should change colors. Taking negative 1/2 of this part and then adding it to row 3. And so that means that we have a row of zeros until we get to our last entry. And that means that we can't have a consistent system. Therefore, the question that's asking, is the equation AX equals B consistent for all possible B1, B2, and B3? We can say no. That silver's kind of nice. All right, so we got another theorem. So if we have M by N matrix A, then we either have all or none of the following things. And we're going to have this kind of like a snowballing thing. So we're going to have, logically equivalent things is going to be fun. So for each B in Rm, the equation Ax equals B has a solution. So a solution exists, and if a solution exists for Ax equals B, then we also have that each B in Rm is a linear combination of our columns of A, and our columns of A span Rm, and A has a pivot position in every row. So that means we don't have a row of zeros. So we either have all of those things or we have none of those things. So if you can show that, your columns of A don't span Rm space, then you can also say, well, like A doesn't have a pivot position in every row, and we don't have a solution for Ax equals B, and for each B in Rm, we don't have a linear combination of our columns of A as something that we can get for each B. So, let's look at this. When we have Ax, and we have this, well, all we need to do is weight our columns of A with our x values. So there's our second column and our third column. And there we go. But can we simplify this more? I think so. So we can distribute this. So we get 2x1, negative 1x1, and 6x1. And you can do these all separately, but then eventually we're just going to add them together, right? So we can also add 3x2s, 5x2s in row 2, if I remember the x, and subtract 2x2s in the last row, and also add 4x3s, and subtract 3x3s, and add 8x3s. And there we go. We have Ax. There we go. We multiply. If the product Ax is defined, then our ith entry in Ax is the sum of the products and the corresponding entries from row I of A and from the vector x. So as long as we have ax, like that's something that we can do because our dimensions work out, then our ith entry of our vector ax, of our product ax, is going to be the sum of your products from your corresponding entries from row I of A and from our vector x, which you can see here. So like the first entry our first entry in our product is looking at our first row of AI, of A. That's A's first row, and our weights from our vector x. All right, let's look at some examples. So first of all, let's make sure that we can compute this this product, because we have a 2 by 3 matrix, 2 rows, 3 columns, and we're multiplying by a 3 by 1 vector. So the dimensions work. We have enough weights to match with our columns. We're going to end up with a 2 by 1 matrix. So what do we get? 4, 0, plus 6, negative 15, plus negative 7, 21, and I think we did this already. We get, what is that? Oh, no, we were supposed to do this with our rows. That's my bad. So that was the old way of doing it. A new way of doing it is by taking our first row and weighting that with each of these. So our first row of A is 1, 2, negative 1. So 1 times 4, that spot is 4, plus 3 times 2 is 6, plus negative 1 times 7 is negative 7. That's our first entry, and then our second entry is our second row, multiplied by these weights, so we get 0 plus, that's very small, 0 plus negative 15 plus 21, and so that gives us a result of 3, 6. Cool. Let's make sure this works. We got 3 by 2 multiplied by a 2 by 1, so we're okay. And the first row is going to be 4 times 2 is 8, minus 3 times 7 is 21, 4 times 8, 32, minus 0, okay. 4 times negative 5 is negative 20, plus 14, and so we get negative, did we do this one already too? I think we did. Negative 13, 32, and negative 6. And then here, this one is special, because look at our columns and look at our rows. We only have one non-zero entry in each of our rows and columns, and that non-zero entry is 1, which is lovely. So whenever we take when we're multiplying like across our rows with these weights, we're going to end up with R plus 0 plus 0, 0 plus S plus 0, and 0 plus 0 plus T. So what we had before and what we multiplied by, they were the same. So just like when you have 1 times x equals x, when we have our vector, or when we have our matrix where we have 1s on the diagonal, 0s everywhere else, by some vector x, we're just going to get out x. So this is called the identity matrix. Identity matrix, and in MATLAB, it's like EYE, and then you put like the dimensions of how big you want it to be. I think it'll make it a square. So if you say like I of 3, then it'll make this matrix, this identity matrix with i's down the diagonal and zeros everywhere else. Alright, so if we have m by n matrix and u and v are vectors in our n space, and c is a scalar, then our matrix multiplied by the sum of u and v is equal to our matrix like distributed to a times u plus a times v. And when we have our matrix A, we're multiplying it by some scaled up version of u, then we can take that scalar and multiply it later. So we can have the scalar multiplied by our matrix multiplied by our vector. So that's nice. I think you can probably justify those to yourself. Because if you, like, suppose that you had n was like 3, then you could just show symbolically, you could justify that. So, yeah, maybe if you want to do that as a journal entry, that can be a cool journal entry. I think that just about does it. Also, if you watch The Matrix and then you just, like, want to write about that, that can also be a journal entry. Alright, that's it. There is no spoon.